Hi everyone, thanks for watching and welcome to Past Physiology Review of Topic 2. In this video we'll be looking at the table which compares tendons, ligaments, and cartilage, and there's a lot here, so I encourage you to maybe go back through this twice, look at your own notes, and be looking up pictures of anything that you can look up a picture of as we do this or afterwards. So let's get started. First off, all about tendons, its components and structure and functions and random comments. First off, I've got a little picture here to kind of show you the arrangement of tendons. You have multiple cords kind of running together, okay, in an arrangement like this. Collagen fibers are bundled up in bundles to form fascicles, and they're surrounded by loose connective tissue. And then those bundled up fascicles will form a tendon, which is covered by a dense irregular connective tissue. That's what these parentheses are for. And then you'll have so this picture is kind of referring to this over here, okay? So collagen fibers, you could call these fascicles. Say there's a bunch of little fibers. This could be a fascicle. And so all these different bundles of tiny little collagen fibers, these are all fascicles. This makes one big tendon. And then you've got coatings around it. The epitendinium will coat the tendon, so that would be all the way around it. And then in certain places in the body, you'll have a synovial sheath, which is just two layers of epitendinium to allow for easy movement through different places in the body. So that's what this little picture is about, and since it can be complicated, I want to mention that right away. So what do we have with a tendon? We have dense, regular connective tissue, same as a ligament. We have very little ground substance because we have a whole bunch of collagen fiber. We don't have a whole bunch of water bound up in sugar, okay? We have lots of fiber instead. You've got type 1 as the most common, and that might be worth remembering, okay? Most common things are good test questions, okay? So type 1 collagen is the most common thing you'll find in tendons. That would kind of make sense because if you remember back to the collagen types, you know that number 1 is number 1, most common in the body. It's the biggest, it's the strongest. And what a tendon does is it provides movement because your muscle contracts and the end of a muscle, okay, it blends into this thing called a tendon, which is a rope. So your muscle contracts and it pulls on this rope, which is a tendon, to move bones, to move your body. So I should hope that fibrillar collagen is being used because it's tough stuff. It resists tensile strength, so it doesn't just stretch, okay? Otherwise, that would not make an efficient muscle contraction. You want your muscle to contract, and you want that to pull on a tough rope so you don't lose, very much energy with that contraction. You can have some elastin though, and you can have some reticular, inky-dinky, little type 3 collagen. There will be fibroblasts, fibers, blasts making stuff. They make new fibers, fibroblasts. Tenocytes, anytime you see the word cyte, it means cell. Tendon. So you have tendon cells. They're a unique thing to a tendon. And you'll have, depending where in the arrangement, you'll have dense, irregular connective tissue coating each tendon as the epitendinium. And you'll have some loose connective tissue around the individual fascicles, okay? So pretend that the collagen fibers themselves are so small you can't see them, but that each of these circles is a fascicle, okay? Around each fascicle, forming the gray line, okay, is right here, loose connective tissue around the fascicles. In parentheses is the covering in this little table. It's kind of confusing, but that's why I'm going over this again. So that's kind of what you'll find in it. Okay, so the structure is longitudinal. They're just ropes. Okay, they're longitudinal ropes as opposed to ligaments are more interwoven. That's a difference, so I highlighted interwoven right there. Tendons can be formed as straps or just straight up cords like a rope, or they can even be found as a sheet, which you would call an aponeurosis. And what they do is connect muscle to bone. So once again, you've got collagen fibers forming fascicles coated by loose connective tissue. Bundled up fascicles, okay, will form a tendon. So lots of fascicles together form a tendon, which is surrounded by dense irregular connective tissue. That dense irregular connective tissue is called the epitendinium. Okay, so I'm going to draw a little line here with an arrow. That was a bad arrow. Okay, but that's the connection for you. Okay, you can draw your own nicer than that. But the dense irregular connective tissue around the bundled up fascicles, okay, around the tendon, is called the epitendinium. It coats the tendon. And when you need it, when there's a lot of movement in the area, you'll have this thing called a synovial sheath. Form, which is 2 layers of epitendinium with some fluid between those 2 layers so it can slip and slide and move. This will be found in joints in the carpal tunnel so that tendons can move through tight spaces and heavily used body parts so that it can move freely without causing a bunch of friction and inflammation, hopefully. So make sure you know what this is. The synovial sheath, 2 layers of epitendinium with fluid between, fluid as in synovial fluid. And then once again, a longitudinal fiber arrangement compared to the interwoven fiber arrangement of a ligament. So ligaments are also dense regular connective tissue because they have to be strong too, and they strap bones to bones. Something special called a retinaculum is kind of a flat band that will strap down tendons at different parts in the body. The flexor retinaculum is on the wrist, and then you have an extensor retinaculum on the front of your ankle, and those are there to hold down your tendons so that they don't go springing up with contraction, and this helps with mechanical leverage and secures things in place. So you'll see these in gross lab if you haven't already, the flexor retinaculum of the wrist, and then later you'll see the same concept at the ankle. Functions of ligaments are just holding the structure of the skeleton together, the bones and joints structures together, okay? It limits the movement of bones as opposed to a tendon. Okay, what it does is it purposefully transmits tensile forces to move bones. So tendons are about movement while ligaments are about limiting movement, okay? You have resistance to tensile forces, so you have tensile strength, okay, in a ligament as well. They have a little bit of stretch, perhaps more than a tendon. Okay, I would hope more than a tendon. They have less collagen and more elastin, okay, and also more reticular fibers. So they have more stretchy stuff than a tendon, which just makes sense because if a tendon is stretchy, or at least if all of your tendons are stretchy, you're wasting energy because it's like you're not gonna want to pull on a rope that's elasticy. Otherwise, you have to pull extra hard. Okay, so just kind of think of that. You do have elastin and some energy storing tendons in the body, and you would have a lot less elastin in positional type tendons in the body. You can get more into that later. The concept is basically, more elastin in an energy storing tendon because it creates the ability for recoil and springing type stuff. Get more details on that later. The epitendinium, okay, allows for easy movement. We've kind of talked about that. And both of these ligaments and tendons are going to have things called Sharpie fibers, which will insert them into the bones that they're interacting with, okay? So there's a lot of similarities and a few differences. So we're kind of talking about them back and forth. They both heal slowly because they do not have an adequate direct blood supply. And they both have Sharpie's fibers securing them into their anatomy that they're involved with. So a tendon connects a muscle to a bone and it attaches into the bone by weaving these little sharp fibers, Sharpie's fibers, into the periosteum coating around a bone. Ligaments do the same thing. They connect bones to bones, and so on both ends, they have these little hooking, penetrating fibers that weave themselves right into the periosteum connected tissue to form, sort of one structure. And if we look at a picture, we can maybe find one on the interwebs real quick here. Voila. Okay. So this is just a picture of periosteal attachments. Nice, simple picture. You got a bone and a joint capsule. Okay. Well, this is the joint space, and here's the joint capsule. So here's like a ligament. You could pretend this is your knee or your elbow or whatever. And yellow is the ligament connecting bone to bone. And then if you see down here, they just drew real simple, which is simple as good, these little fibers connecting the ligament into the periosteum. And what this actually does is it integrates the two structures together. It kind of sews the ligament into the tissue, into the fabric of the periosteum. And the same thing happens with the tendon. So the tendon connects a muscle to the bone, and then it has these little tiny little fibers that come out of the tendon and literally sew the tendon right into the periosteum of the bone, so it has a nice strong attachment. And I think of Sharpie's fibers are sharp and they're hooked in there. Okay, they're really kind of sewn and weaved into it, but sharp is a perforating fiber attaching tendons and ligaments. Okay, so know the differences and know the similarities. Maybe when you're studying, you want to make a little Venn diagram, right? One of these deals with two circles. What do they have in common? Put it in the middle. What do they have separate? Put it on the outside. Kind of an old school teaching thing that's kind of helpful to study with. Okay. Now cartilage, there's a separate video on cartilage details, but I wanted to put this in the same table as tendons and ligaments so that you can kind of compare some of the big ideas. Okay. So cartilage is going to have a semi-rigid extracellular matrix. It's going to have gags that suck up lots of water and make this waterbed thing, but it also has a lot of fibers because it needs to be tough and resist various forces. There's different arrangements and different types of cartilages, okay, but this is kind of everything as a whole. So gags, glycosaminoglycans that you're going to find in cartilage are most commonly going to be hyaluronic acid, the biggest and the most common in the body at all. Okay, it's also essential for lubrication at joints. That's a thing from topic 1. And then chondroitin, cartilage, oitin sulfate. So cartilage sulfate. You read chondroitin, you just say cartilage sulfate. These are the big boys for gags that are going to be found in cartilage. Okay, you'll find, of course, proteoglycans and glycoproteins without names, but you'll have them in there. But know the gags that you find in cartilage. And then what else would you have in cartilage? You need cartilage cells. Chondroblasts. Blasts always make things, so they're going to make the matrix, okay, the extracellular matrix. And then chondrocytes in the lacunae. Okay, so I have this little I here, chondrocytes, lacunae. If that helps you, just to kind of get a grip on, just make a connection between these words. You're going to learn more about lacunae and bones and ossification patterns and things like that. But if you just say chondrocytes are in the lacunae, that rhyme might might save you a point somewhere. Okay, so chondrocytes maintain matrix of cartilage. Chondroblasts make new matrix. Okay, blast means to make. Okay, so the structure of cartilage matrix, lots of fibers, but you still have ground substance that has hyaluronic acid and chondroitin sulfate as the principal gags. Of course, you're gonna have different cartilage cells embedded in the extracellular matrix because that's where they live. That's the waterbed, that they're in. Something else you'll have in cartilage is going to be a perichondrium, except in growth plates and in joints. Okay, at joint surfaces, you won't have perichondrium. Okay, but otherwise, and I guess of course you're not going to have it in fibrocartilage either. Okay, you don't have perichondrium around fibrocartilage. Okay, so don't take the information from this table and let it be the gospel for you, because you still have to keep this stuff straight. Okay, but perichondrium has two layers. Where perichondrium exists, it has two layers. It has an outer fibrous layer and then a deeper cellular layer. The fibrous layer is more superficial, and if you think about it, that kind of makes sense because fibrous means tough, means fibers, basically, okay? And cellular means not tough, it's just cells, so they need to be protected by the fibrous layer. So the outer superficial fibrous layer of the perichondrium is going to have connective tissue of the dense irregular variety, okay, which is going to have a lot of type 1 collagen in there. And it's going to have fibroblasts. That makes sense. Cells that make fiber stuff, okay, fibroblasts, fibrous layer. And it's going to have vessels and nerves and lymphatics. Okay, it's going to have big stuff. It's going to have fibroblasts and big stuff like vessels, nerves, and lymphatics, and it's going to have connective tissue. The deeper cellular layer of a perichondrium is just going to have cells. It's going to have fibroblasts again, and something kind of like a stem cell, a more evolved, a more differentiated stem cell called a progenitor cell, or a pre-chondroblast, okay, which will turn into chondroblasts, which make more matrix to make more cartilage tissue, okay, and eventually these chondroblasts will turn into chondrocytes and continue in this job, basically. So cellular layer just has cells. Fibrous layer is going to have big stuff and fibery stuff. Okay, so connective tissue and fibroblasts as well. Let's try to keep those straight. Draw a little box around that for you. Okay, so, or bracket, I should say. So now, functions of cartilage. It's strong, okay, and flexible. And the different types of cartilage have a little bit different functions. But what it does is it has the ability to deform and reform under compressive forces with weight and movement. Okay, so it can kind of squish and kind of spring back to the original shape to help you move and help you maintain a flexible form. And it can resist tensile forces as well in fibrocartilage around the outside of your intervertebral discs. Okay, as one spot for that. Your fibrocartilage also resists compressive loads as well, though. And then hyaline cartilage specifically is involved in endochondral bone formation in your growth plates or your epiphyseal plates, as well as hyaline cartilage will also be found in joints and rigid structures. And then elastic cartilage is going to be found in any type of flexible structure in the body, like the ear, okay, or the epiglottis. And fibrocartilage is going to be found in intervertebral discs and the pubic symphysis and various other articular discs in the body. So it's going to resist compression and tension at those places. So in cartilage, the matrix is going to not have its own direct blood supply, so we'll have diffusion, okay, supplying nutrition and waste excretion. And the perichondrium, okay, think burrito, the perichondrium is what is going to contain the blood vessels. So those vessels have the ability to, supply the surrounding area because transport happens across those vessel walls. Since it doesn't have its own blood supply, you'll have slow healing once again. So notice this, that cartilage, ligaments, and tendons all have slow healing because they have very little blood supply. There are two types of growth that cartilage is involved with. We'll get more about this in bone, in the bone topic of this class. But interstitial growth is the earliest initial development. So in the womb and going onward while growth plates are open in childhood. It's like a longitudinal type of growth. Chondrocytes in the lacunae will divide and increase the matrix within to increase the cartilage tissue, basically. And then appositional goes out, okay? And this happens after birth and throughout, through puberty, basically. Then also when you have an injury and have to heal and repair cartilage. This is kind of an outward growth. So this is going to be chondroblasts in the perichondrium, at the innermost part of the perichondrium, are going to be just adding matrix layers to the outside. So it's an outward type of growth. So just kind of know, maybe for appositional, the word appositional, basically means outward, away from each other. And then interstitial is kind of more longitudinal, like you get taller, your arm gets longer. Okay, that's what interstitial is. So I'm putting these lines in here for you to kind of, maybe you want to do the same thing. Okay, so that concludes topic 2.